Okay, so we start. Let's see. So, first of all, the next assignment has been posted again, as usual. You do it as you see fit. If you want to get it sort of reviewed, we're calling a pre-submission deadline. That will be November 1st. So you have a bit more time to get that. And remember, the deadline for requesting review of your first assignment is coming up. So make sure if you need to use that. You don't have to. If you need to use that, make sure you have a chance. I will also be posting fairly soon, I think, the set of questions for video algorithms. So the second assignment is all about programming. Third assignment will be video algorithms. Fourth assignment will be close. Let's see. So there was a question on the forum about perfect matchings from Tuesday's lecture. So I just wanted to talk about that a little bit. That was an interesting question. Even I can say more. So, where is Charles? Ah, there you are. Okay, good. So, let me. Okay, so for some reason the sketch is not. Ah, okay. I thought it was an interesting question that we were. So that was interesting to discuss this up here. So just because I was thinking about this on the way, and I was like, I'm not sure. So I think the claim that you had, which I think was an interesting claim here, was that. For some reason, this is not fully. The rest of your text is not showing. Is that what you wrote?
Yeah.
Okay.
It's all.
So, can you explain what this idea of a non-repeating sequence is? So, see if we can discuss this a little bit here. This idea, what do you mean by a non-repeating sequence search?
It's actually, I'm trying to visualize in DAG and search in a cyclic way.
Okay, so you have two sides. You have left. So we're talking about perfect matching, and we're discussing whether there's another way to think about how to solve the perfect matching problem. And so you have the left nodes and you have the right nodes, and they have numbers. And let's say there's 1 through n, 1 through n. Okay.
So the non-repeating sequence is actually finding a sequence of the length n, and it contains no repeating element.
So what is a repeating element?
A repeating element is just like if we select one on the right side. I mean on the right side.
Yeah.
Yeah. We select one, and next we select say we select three. We select
on the right side. Yeah.
The search is on the right side.
So if we could all, I can hear also murmuring in the background, which I think it's a bit hard to decorrelate these conversations. Okay, thank you. So
if we select one on the right side, and next we select 4 on the right side, which is the third row.
Okay, this one?
Yeah.
Okay,
then we can select 4.
Yeah.
So we stuck, and we need to retreat and go again.
But I guess I don't understand something. What do you mean you're stuck? So you pick this one, and how do you decide to pick this next?
It depends on the algorithm.
But what is the algorithm? I guess that's what I'm asking. What is this algorithm that you're applying?
We can keep a boundaries actually.
So it sounds like you're trying to find a long cycle in this graph.
Yeah.
Right?
Yeah.
You're trying to say that if I can find a cycle, then that will be a perfect match.
Yeah.
Right? Because essentially, if you think of a perfect matching, and if you think of it as a permutation from the left to the right, it's basically a permutation that gives you one complete cycle.
Yeah.
No.
Actually,
that's not true though.
There's no cycles. If there's a cycle, that means we pick we're selecting a node from for 2 times or 3 times or something.
So you want to select a cycle on one side. But it's not clear to me how you're choosing the next node to pick. That's not completely clear. You have some implicit algorithm in your head, but you haven't made it very precise. So I guess I think it would be interesting to say, okay, can I make this thing in your head about how to pick the next node a very precise statement that is not based on, well, I just look at it and do it. And then you can try to evaluate whether this is going to work or not. Then at that point you might be able to decide, okay, is there a bug in this or not? Because once it's fully specified, you can see if there's a bug. If it's not fully specified, you can't tell there's something wrong with it. And that's a point I wanted to bring up. There was something interesting going on there, but I wasn't sure. It wasn't well defined enough for me to tell if there was something interesting going on. So, but I would encourage you to think a bit more, maybe edit the note and see if we can talk about this more. Okay, good. All right. So that was just a little note. And again, I may not always bring up what you post in discussion in the class. I just thought it was interesting, so I'll talk about it. But feel free to use the discussion that some of you have been using. All right. So let's continue. Okay. So I've been talking, for 3 lectures about network flows, and I've been saying all along that one of the reasons why we like to learn about flows is because it gives us a way of thinking about problems that's not. It's a much more indirect way to think about a problem, but it also gives us a lot of power. There are problems where it would be very hard to solve the problem if you didn't know that such a thing as a flow existed. And so often you'll find problems where you didn't really expect to see a flow formulation show up, actually does show up. And so we're going to talk about a couple of those applications today. And in the notes there are many more. And in the homework, when I give it out for this module, you will see that the main question is going to be how do you map a problem, for the most part, into a flow formulation. There will be maybe a couple of questions that talk about the flow algorithms in detail. But for the most part, it's going to be a modeling. Okay. So let's look at a particular application of network flows. In fact, there are a couple of applications in this domain that use ideas from flows. Some of them are more complex than others. So the first one I'm talking about is a problem called image segmentation. It's a very simple problem. So those of you who may work in this area will be shocked and appalled at the elementary nature of the problem I'm describing, because real image segmentation is much more complicated, which is true. But this again is a simple example to illustrate how you could do something, even very simple, just using simple ideas. So the image segmentation problem, if you haven't seen this before, is to take, you can think of this at many levels. At the most basic level, you have an image and you have a notion of what's foreground and what's background, and you'd like to separate the two things. So apparently in one of the first DARPA challenges where you have these cars that were driving themselves across the desert, one of the biggest reasons why the cars were going off the road was because they were driving in the desert, and there was very little way to tell what was foreground and what was background. Everything kind of looked the same. The sky was this kind of weird orange color, the ground was this kind of weird orange color, and they just didn't know how to navigate. They of course fixed this in subsequent years, but that was a big problem, foreground, background distinguishing. So for example, in this picture, you might want something like this. Like you might say, okay, this is the foreground and that rest of it is the background. You'd like to segment your image. In other words, you're going to take every pixel and say, this is a foreground pixel, this is a background pixel, and so on and so forth. Again, it's a very primitive view of what you need to do with image segmentation. You might want to do edge detection, you might want to do all kinds of other stuff. I'm not talking about that. So, if you can try to formalize this problem. You can say, okay, I have this problem image segmentation. I would like to formalize this in some abstract way so I can try to apply some algorithmic methods, whether they're flows or not. But just as described, it's kind of very vague. I need to be more precise about it. So to be more precise, you might say something like, I have some image, and it has n pixels in it. Okay. And I want to assign some kind of foreground and background belief for each pixel. Now you might say, well, if it's not foreground, it has to be background. So these two numbers are not independent of each other. But let's say for argument's sake that I would like to different notions of belief for these things. Maybe I have a pixel that has a very strong belief in being both foreground and background, which means I'm very confused about it. And so I'd like to keep that option open to myself of not being sure, without my not being sure in foreground implying that I'm very sure in background. So I want to compute some numbers, some AIs and BIs, which would represent a belief. So the numbers would be bigger if I felt more strongly about the fact that they were foreground and background. And so this is what you want to do. Assign those pixels to foreground and background to align with your belief. And by itself, this might not be a particularly hard problem. This is kind of very under-constrained. Because I could say, oh, okay, look, I have 4 background pixels there and 5 foreground pixels here. I just figured this out. And you look at this and say, that's possible. but it seems unlikely. For the most part, you expect a foreground piece to be contiguous, to be smooth. And again, these are approximations. These are modeling assumptions you're making. They may not always be true. But as a first approximation, let's say I want something like that. So you don't want some kind of checkerboard pattern like this, where you say, oh, I just let the foreground and background pixel be completely uncorrelated with each other. I want some sense of correlation. That if this is a foreground pixel, there's a good chance something nearby will also be a foreground pixel, until you find it. Okay. So now you might say, okay, look, I have some notion of closeness. I have some notion of closeness that says things that are close, I expect to have the same label, for the most part. So you have some neighbor relationship, Pij, which gives you a number that says they're close or not. You could think of this as being an edge between or something like this. And now you have a slightly modified question that says, again, I want to assign pixels as foreground and background, but I want to preserve continuity as much as possible. Okay, and again, I don't yet have a formal definition of this problem, but I'm getting better. I've got a bit more precision in what I'm trying to say. Now it's a question of taking all this English and converting it into a mathematical expression. So far, is it fairly clear? Okay. So let's sort of formalize this. And again, this process I think is very useful to see how this works, because this is the kind of thing you do all the time when you sort of model a problem as an algorithmic question. So you have a set of pixels, okay, some set, and you have some solution set, which is foreground pixels, you have some other complement set, which is background pixels. And now you want to maximize belief for the foreground. So for every pixel you declare to be foreground, you want to maximize this number sigma AI. Right? So I have some other, so what I should have mentioned was I have some underlying process, maybe some learning algorithm, that has given me some sense of an AI for each pixel, and some sense of a BI for each pixel. Right? But that doesn't mean that I know they're foreground back. It's some algorithm, some learning algorithm ran something and gave me something. I don't know. And I want to convert that into an actual determination. And so I have some numbers here, so I'm going to choose these things. And similarly, I want to maximize the belief for the background. Right? And so again, I could look at each pixel and say, pick the maximum value, and that's my belief. But of course, that's going to create all kinds of checkerboarding patterns. Right? I may not actually have a nice smooth behavior for this thing. So on the third parameter is minimize discontinuities. Right? So in other words, if you look at all the pairs of nodes or pairs of pixels that have one endpoint in the set and one endpoint outside the set of foreground set, these are pixels that now you have declared that were deemed to be close by this Pij relationship, but I've declared to be in different sets. One is foreground, one is background. And so I must pay a price for this. Of course, if Pij is 0, then it means I didn't care that they have to be labeled differently, so I don't pay any penalty for it. But if Pij is very large, then I'm saying, no, I really want these pixels to have the same value. You put them in different buckets, this is going to be a problem for me. So you have to penalize them. Okay? So now you have these terms. You want to maximize the first two, you want to minimize the third. And if you have an expression where you want to maximize a bunch of things and minimize a bunch of other things at the same time, the simplest way to combine them is linear. Just say this is my function. I want to maximize f of a. So a is my set, right? I'm going to choose a set of foreground pixels whose complement will be the background pixels. That's my output. And I'm going to assign a cost to this choice. And this cost f of a is going to be this cost here. It's not a cost so much as a profit, I guess, because I'm maximizing. I'm happy when I have good assignments here. I'm happy when I have good assignments here. And I'm unhappy if I have large values here. And for any a, you can define this number. So now it's just a matter of searching through all a's and finding the best, the one that has the best number. Does that make sense?
Excuse me, that sigma AI means that the number of pixel which is
no.
For
AI is a number assigned to each pixel. That is a number that is larger if you feel more confident that it's a foreground pixel. It's smaller if you feel less confident. This is an input. It's coming to you from some other place. So you don't have to search for this. They're given to you. I think I gave the wrong implication. I gave the wrong impression of it. So the AIs are given to you. The BIs are given to you. Your goal is to find the set. You had a question back there?
Pij, how we define it? If A and another A is separated by a B pixel, we say that it is discontinuous.
So Pij is given to you as well. Pij is part of the input. It's saying this is my baseline sense of what neighborhood means. For example, I could say every pixel is neighbors with the 8 pixels around it. Okay? And so the Pij for any such pair will be 1. And the Pij for any other pair will be 0. That could be one way of interpreting this. Which is saying basically I want close proximity. Or I could say, no, I know something about my image. I know that this whole section here is probably where the foreground is. And so all the Pijs here should be small, but for the rest of it I don't care. So there are different ways. So again, there are modeling assumptions I am putting in based on what I know about the domain that are going to be factored in here into these numbers. And then I want to solve this optimization. Yeah.
How is having a high background belief different from having a low foreground belief?
Because the AIs and BIs are different. I might have one process that's doing foreground detection. I might have a different process doing background detection. And they're separate from each other. Again,
we don't care about that.
We don't care, it just gives us the numbers. And here's the point. You could say, no, in fact they're correlated, and you could change this. That's up to you. So this is just one choice of modeling here. It's not the only one. Yes?
When you're maximizing it, are you getting from one, let's say when you process one image, are you getting one set of EAs, one set of EAs, and then you process it again? And PIJs. And then you process it again, you get different set of EIJs.
That could happen.
Because you're saying maximize, like what can you do?
I'm maximizing the set of the final choice. This is the choice of foreground background. Right? Once I solve this maximization, I have a set of pixels marked as foreground. I color them with a green, like I showed you in the first picture. Those are my foreground pixels. That's what I present to the user.
So would you throw away some of the pixels?
It depends on how. It depends on a couple of things. Right? First of all, is my modeling good?
Okay.
Are my numbers good? And then is my optimization good? There are many things that are going to go into that final issue.
I think the question is if I have n square pixels,
Yes.
would the maximize function go over all the n square pixels? Or?
Okay, so now you're asking an algorithmic question. How do we solve this problem?
Okay.
We will get to that in just a second now. That's a good question, but we're not there yet. We're still making sure we understand what the problem is. So in all these things, right, and this is something that I often tell people, make sure you understand the problem before you start worrying about the solution. We're trying to understand the problem here. Yes?
The discontinuity point, so we are taking A intersection of Ij.
Yeah, so this is a little mathematical artifact that is a way of saying in mathematical language things across the boundary. So we're saying, okay, what is this? Look at the set of pairs Ij, so that A intersection Ij has cardinality 1.
So something is.
It's basically something's inside, something's
in
outside.
both ends.
Yeah.
So my question is, why are we considering only the foreground pixels and not the background ones? Like B intersection Ij, why?
Because it's the same thing, right? Because A and B are complements of each other. B is the complement of A.
Okay.
So it's the same thing. Any other questions? Yes.
Assuming that A is, let's say you have a high belief that a pixel is a foreground, could you also have some belief that has some small belief that it could be a background?
Absolutely. It could happen. That's why I separate them out. So in other words, if you suppose you have a pixel that has an AI, BI values, and they're both something, you decide to call it foreground. You get whatever profit you get from declaring it to be a foreground pixel. You don't get any profit from its background belief, so you lost that. And you may or may not pay a penalty for the fact you turned this before.
Would you repeat that statement? Penalty for, what's the exact phrase? Penalty for being wrong about?
Yeah, so it may be that your choice of putting this in the foreground means that a bunch of the pixels that were background around it, you know, you declared them in background, you decided this was a foreground pixel, and now you're going to pay a penalty for the fact that this foreground pixel is right next to all these background pixels.
Okay.
And our PIG is trying to capture the idea that we don't want this to happen more or less. And it will happen, right? None of these things are going to be 0, but you don't want to make it small. Because you expect at boundaries, that like an edge, there will be some crossover. That's okay, but you don't want to be too much. Good, yeah.
What is PIJ?
Again, PIG is a number that says, it's a number given to pixels. INJ says, how close are they? If I believe that they should be viewed as close, that means they should be part of the same set, either foreground or background, this number will be big. If I believe they're not, this number will be small. This is input. This is given to me from some other process. Right? all my goal here is to make sure that if I do believe things are close, that I want them to have the same label. And this will penalize, allow you to penalize things that have different labels for it deemed to be close, because I'm adding up all those P and labels.
So,
Yes.
one question on that. But so if you actually are finding an edge, you are going to have background and
I will, and I'm
foreground.
going to pay some penalty for
So
it.
you expect some penalty.
Yeah, I just want a lot of penalty.
All right.
Right? I mean, that is, yeah, again, it all, yeah. One way to think about this is that, you expect that the largest value of Pij will be for things that are right next to each other, and as you go further out, it'll decrease. So, for example, have you ever done Gaussian blurring with an image? Any of you ever played with that? A couple of you, yeah, a few people there. So that's one way of thinking about it. So as you go out further from a pixel, the influence kind of decays with time. So you don't expect two pixels that are very far apart to have the same foreground label, or required to have the same foreground and background label. They might, or they might not, but I don't care. And so you can think of many different ways of modeling this. This is again a modeling issue. Right? And it's important to separate these things out. How I model the problem gets me to this point. And then I solve it. You want to make sure you model it in a way that you feel is reasonable before you go about solving it, because you're solving the wrong problem. Okay, so far so good. We have this function now, and we'd like to optimize it. And since we're talking about flows, we might think, okay, is there some way to think about how this might be a flow problem? And one clue that's here is that we're doing something with sets, right? If you remember your flow formulation, we know that there's these max flows, but there's also in cuts, and a cut is a set. And here there's a set. So at a very basic level, okay, there's something there that might be useful. Okay, but does it really count? So you want a set. So maybe I have to do some kind of cut. And so the typical cut problem is I want to minimize some cut. But I'm not minimizing, I'm actually maximizing. So that doesn't work. And in fact, as we'll see in a few lectures, max cut is a very hard problem. So min cut is easy to solve. We just saw how to solve it. Max cut is much harder. It's an engineering problem. So this is not a good sign. That may not be a good sign for our ability to solve this problem. And we have some kind of graph because we have neighborhood relationships between nodes. You can think of an edge between two pixels, the base and weighted by Pij. But it's undirected, it's not directed. And I don't know what an edge capacity even means in this context. And there's no source or sink. So how on earth am I supposed to map this into a flow formulation? There's no reason at all why this could be solved by a flow. And when you see a problem and you think, okay, can I apply flow to this? Most of the time it'll be something like this. That there's no apparent reason why this should work. And I'm not here to tell you that there's an obvious reason why it will, you just don't see it. There isn't one. But you have to try different things. So we're going to try a bunch of stuff. And there are some simple tricks you can try to see if you actually end up with something that's flow. So let's look at the function here. So if you look at our function carefully as FA function, and define this quantity called Q, which is the sum over all pixels of the sum of their AIs and PIs. Don't worry what this means. I'm just doing algebra. Please add up all these things. Okay. So now if you rewrite FA explicitly, what you'll see is that FA is sigma AI, I belong to A, sigma BJ, J belonging to B, minus the cross term. And you can rewrite the first two, forget the cross term for a second. Just look at the first two terms. So the first term can be written as the sum of all the AI minus the sum of the AIs for things in B. Right? And similarly, the second term can be written as sum of all the BIs minus the BIs for things in A. So you're looking at the background belief values for things in foreground and vice versa. And then if you arrange the expressions properly, you get this expression here. And now you get this. That f of A is a constant, because Q is a constant. It's a function of the input only, minus some other function of A. And so why is this a good thing? If I have to maximize the f that is equivalent in minimizing G. And again, we got lucky. Right? We just got lucky. And half the work of solving the problem is getting lucky. But we were able to recast this maximization as a minimization. And intuitively, I mean, it's not completely luck, because what you're saying is that instead of maximizing the profit, I'm minimizing the loss. Right? I'm saying I took a pixel that I labeled as background. My loss is its potential foreground value. I took a pixel and labeled it as foreground. The loss is its potential background value. So I'm just keeping everything as a minimization. I want to minimize those losses. And I was minimizing the Pij. So now we can have a new problem, which is minimizing G. And G is a function of a set. So we have to find a set that minimizes something. Right? And so now we're a little bit happy because now we're not maximizing us over a set, we're minimizing over a set. It doesn't mean we have a solution, but progress. Okay. So we have a, so remember these are the checkpoints of things we didn't have. And now we have the first one. So we now minimize. And now we have to deal with the graph being undirected and non-directed. And again, this is a simple trick. If you have an undirected edge, and think of this as an edge between two nodes labeled by Pij. Just replace it by 2. And since the only numbers I have on edges are the Pij's, we'll call them the capacities. Why not? That's the only one we have. So we assign all edge capacities as Pij. Okay, so now I have this. And now we have a source and sink. I don't know who to connect it to. We'll just add them and connect them to everyone. Again, just because. I'm not saying these things will work, but you'll often find that when you're trying to solve problems, that this might be a good first way to start. And then you'll see problems occurring and you'll try to fix them. So we connect the problem. So what do we get at the end of this process? We have all these things, and we have what we want. Now we need capacities from source and to sink before we can even call this a flow instance, let alone have it be meaningful. And that's where things start getting interesting. So let's look at this function again. So we had these vertices in this graph are the pixels in our image. We put an edge between essentially every pair of pixels that has a non-zero Pij value. And if they all have non-zero pages, you'll have every single edge, possible edge between pixels in the graph. You're always shuddering at this point because your pixel has, a million. If an image has a million pixels, this is going to be a million squared, but let's not worry about that for now. And so now once you have these edges, we want to minimize this function, Q of A. We also know that since we're minimizing a function of a set, what we'd like to have happen somehow is that big number becomes the cut value of the set. It has some kind of capacities attached to it. So if you fix an answer A and B, what you'd like to say is that QA, that whole cost function, is equal to the cut value of A. Because then we can start trying to minimize it. So I'm trying to retrofit now to the modular problem. So let's look at the Pij's first, because that's the easiest one. We're summing up the Pij's for all edges that go out from A and come back into A. Or that go out from A, right? Remember I said the capacity of every edge was Pij in both directions? So if you look at all the edges coming out of A into B, what is their capacity? It's Pij. So that means that term takes care of all the capacity of the edges coming out of A already. Again, we don't know what A is, but whatever A ended up being, that's what it's going to take care of. So the Pij's capture that part of it, all the edges from A to B. But we've got to worry about all these other edges as well. So the edges, S is going to be part of A. So there's going to be edges from S to B, and there's going to be edges from A to T. How do I take care of those? What should I do? How do I label these edges with capacity so that Q of A magically becomes the cut capacity of the set A, including A? That's the question.
Could you label the edges that go to the sink with A of I, and the edges that go to the source with B of I? No, actually, I think it should be reversed. So then if
Anyway?
I have a question. So you already labeled the edges that are going from A to B as Pij's, right?
I did that earlier, right? I said every edge has a capacity Pij going one direction, Pij going the other direction. all the way down.
Okay, now we want to know what should be the source to A, the source.
Right, we don't know the capacity is BGP. And we would like to make it so that when we finally do find A, remember A and B don't exist here, they're in our head. They're not in the problem here. But when they do finally show up, that QA will be exactly the cut capacity. So that minimizing the cut value will be the same as minimizing QA. That's what we want.
You have PIJs when you're evaluating insert AIs and B.
Correct. So,
Yeah, so I think that would work if you label the edges that go to the sink, or excuse me, the edges that go to the source,
from the source.
yeah, from the source,
With,
A of I,
okay,
and the edges that go
oops,
to the sink with
Yes.
B of I.
okay. Let's just bring the picture back up. So this proposal on the table right now is to say every edge going out from the source, remember I said the source connects to everyone? So the edge from the source to the pixel I should be labeled with AI, and the edge from any vertex to the sink should be labeled with BI. Notice that I can do this ahead of time. I don't need to know what A and B were. Right? This can be done ahead of time. I just told you how to do it. Is this correct? So let's look at now an actual answer. I produce some set A, some cut, which includes S. What is the cut capacity? So there are three kinds of edges. Edges going from A to B will have cut value, total value, some of the Pij of edges that have one endpoint. So that's one. Edges going from A to T, right? We said should have capacity Bi. So you're going to add up one Bi for every edge in A. Look at that second term. Sigma I belonging to A Bi. That's exactly what that's going to be. Now there are going to be edges from S to B, which are also in the cut. And that will be just the sum of AI for those edges, which is the first term right there. Right? And now every edge is accounted for. So in other words, we have created a flow instance, which we can create without knowing the answer, which is the whole point of this. Right? We can do all of the stuff syntactically ahead of time. So that whenever we compute a cut, the value of that cut will in fact be QA, by the way we've chosen these values. Yes?
Can you please explain how you have drawn this graph? Like you said that source should reach to every other vertex. So why doesn't it reach to the vertex in A?
Because if I drew them all, it would be totally cluttered. And those edges don't contribute to the cut value. I wanted to draw only edges that contribute to the actual cut value. And the only edges that contribute to the cut are the edges that go out of A. And so I didn't draw all. You're right, though, they are missing. It would have been extremely messy if I didn't draw them all. But yes, the edges I'm marking out here are only the edges that contribute to the cut. So once again, the cross edges give you Pij. These edges give you AI. And these edges give you. That's key. Okay. Yes.
So if let's say AI is significantly smaller than BI or Pij,
Sure.
right? I mean, aren't you going to have a bottleneck there, and then you might not have all the edges in the cut?
Am I going to have a bottleneck because I put at a single edge of capacity AI which is really small?
Yeah, right.
Yes, I will. But it's one edge. There are other ways to get to B.
Okay.
Because S has got an edge to everything in B. And everything in A. Right? So if you're saying that this value AI is very small, then you want to put it in B.
Right.
If AI is very small and B is very big. And then if you get to it through some other method, you can push all that flow on to T. Well, sorry, let me say it again. Sorry, if AI is small, then it's the edge from that, if then you put that in B, its edge to T will have a very small capacity.
Right, sorry.
Its edge from S will have a very large capacity.
Right.
So that is what you want to put in there. If you put in A, then you might have problems. Make sense? It's a little tricky to reason about individual nodes here because when you're doing a flow, you're doing some kind of aggregate computation. So something that happens here will presumably get balanced out by something that happens somewhere else in the graph. And it's hard to reason that this itself is going to cause a big problem. The trick is not to think about it at the local level. You're doing this in aggregate. And then you rely on the flow magic to sort of solve that, optimize that question of 10, which is what you want to solve. Right? It's not, any particular pixel might be better or worse assigned. But you're trying to solve the aggregate problem. That's all. Okay. So at this point, we're basically done. We have, so our modeling, our solution to this problem via flow says, take my input, which is an image with n pixels and AIs, BIs, and PIJs. Construct a graph which has one node for each pixel. It has two directed edges for each undirected edge. And now again, you might say there weren't any edges in the original problem. That's true. In the initial problem, I imagine I have edges between every pair of pixels, labeled with PIJ. And that's PIJ is a 0, you just delete the edges. But in principle, you have an edge for every pair of pixels. You replace that undirected edge in those two pixels by these two directed edges, each with capacity PIJ. Again, you can do this just from the input. You add edges from source to each pixel with capacity AI. You add edges from every pixel to sync with capacity BI. Again, something you can do ahead of time. And then you solve and then the min cut will be your foreground. Done. So all the work here, which is very strange, right? All the work here is in taking your problem and munging it into a form where you can apply flow. And the flow becomes a black box. Yeah.
So in this problem, the flow will be Q of A, right? But I still have to...
No, that's a cut. It's also the flow value, yes. But
it's not the flow value.
Yes, because min cut is equal to max flow.
I want to find minimization on different values of A. Different sets of AIs and BIs, right? And PIs.
Why? For any instance, I have a fixed set of AIs, BIs, and PIs. What I'm minimizing is overall choices of actual foreground, background determination. So I start off with the AIs, BIs, and PIJs. What I want is an assignment of each pixel to foreground or background, foreground or background, foreground or background. That's my output. It's a binary thing.
Oh, you want to find the cut such a way that, oh, okay.
I always like when someone says,
So in some sense, if there's one pixel, if this is not giving a minimization, if I push that one pixel into B and then I get a minimization flow, is that the minimization cut? Then that's the minimization cut, I think. That's the answer.
Yes.
Okay.
The flow algorithm just produces the min cut.
Oh, yeah.
By the way, how does the flow algorithm produce min cut? Pop quiz.
Because it can push.
Anyone else? Anyone? Sorry, I heard mumbling in the back.
You start at the source and you go to those vertices that are reachable from the source.
Thank you. Just make sure. So that's what they did to do. So you take this problem, you take the graph, you run the flow. You don't want the flow value, you want the cut set. You don't even want the cut value, you just want the cut set. And that's the second thing. So flow has this kind of double thing, right? Where you can either be trying to optimize a flow or minimize a cut. And for your problem, it depends on what you want to do. Okay, that after some practice, you will get some sense of how you want to do this. So they're both. Are there any questions about this?
Who came up with this algorithm, and did they use this technique to originally solve the problem?
I don't think this was used to do image segmentation because image segmentation was kind of a well-established, at least, area. But this is actually from the Kleinberg-Carter's book, this example. But there are slightly more complicated variants of this idea that are used for doing image segmentation. If any of you work in computer vision, have heard of the NCut algorithm. It's a more involved version of this. You have all these wonderful things like graph Laplacians and all showing up. But it's basically the same idea. That you take an image and you want to segment it into pieces. You think of that as a clustering problem. That I want to cluster the pixels in the image into two groups. Then you define a clustering problem by modeling the image as a graph, much in the same way. And then you do some more complicated things with it. It's a generalization of max flow. It's beyond the scope of what I can talk about. But I can tell you about it offline if you want. Email me, I can send you a reference. It's a very nice, it's a paper from 2001, not that long ago, by Shi and Malik, and they first sort of thought of this sort of spectral viewpoint on image segmentation. And it's been that has been very used a lot in the image in the vision. Yes?
How can you extend it to multiple images in a
with like multiple foregrounds?
Sure. So you could, but the question is, what is wrong with just running this algorithm over and over again? For each image, I have its own AI, BI, BIJ, right? And I run this algorithm again. So new image comes, I run again. New image comes, I run again. Would that suffice for yours, or are you thinking something different?
I'm just thinking that we look like some other new like AIJ, BIJ, there'll be new variables that will be added.
But why? So the question is, why do you think that dealing with multiple images is different from just running the same algorithm over and over again for different reasons? So that means you're making some assumption about the images being similar in some way. Is that what you're saying? Okay, but that's, for example, you might say I have a video sequence, right? I have a video sequence and I want to do image segmentation. Now I could, of course, take every frame and run this, but that would be kind of dumb because from frame to frame, the image doesn't change much. So you could say now my input is a collection of images, like the way you're saying, but I have this kind of temporal coherency. And I want to do segmentation in such a way that, what I want, for example, what I would want is that I don't want my answer to change a lot from frame to frame, because there's no reason it should. Whereas this algorithm is blind, it will give a completely different answer next time I run it. Right? So I could have, foreground, background, foreground, background. It doesn't really know what's going on. However, if I have that constraint, I might say there's some kind of smoothness constraint that says, from image to image, the foreground value should not change a lot. So I might return one more cost function. Right? So I might say my input is a collection of images, I have a smoothness constraint across images, plus all these constraints for a single image. Now I want to optimize it, I have some function, can I solve it using flows? And maybe you can, maybe you can't, I don't know. But that will depend on how you model it. But that's one way of addressing the issue of what to do with multiple images, if you have video. I don't know if that was if it was way out of track of what you were asking. That's what came to mind when you said multiple images. So is this process clear? I mean, again, at a more mundane level, you'll be getting questions in the homework you'll be doing something. At a more important level, this is how you could try to think about flow abstraction. So we're going to take a short break, maybe 2 minutes, and then we'll look at another example of how you might model problems. The reason see how much would work. I want to check. Things I talk about in class for the most part, and maybe that's without I know what I mean. But things that I haven't talked about, are you guys looking? Maximize this credit. Yes. Make it big. No more points. I want to increase the belief. I want to choose points that are high. Correct. That's but I want to make sure that for the most part, I keep them in contiguous blocks. I don't want to have a checkerboard. This is saying don't put checkerboards. This is saying if I believe in their foreground, I should probably make them background. If I believe their background, I should probably make them background. That's what these things are. No, it's actually sum of AI for AI. It's just something over the foreground, just something over the background. pixels you believe to be in the foreground become the background. The pixels you believe to be in the background. So that's the kind of a lost opportunity. You want to minimize the loss of this. So what you're saying is that ultimately we want to find the sense A. Suppose I find a candidate set A, right? How do I want to evaluate its value? This is the way to evaluate its value. By algebra, it looks like it also reacts as that, right? As that thing you want to minimize. So why do you want to minimize the thing that's set? Because we're saying that for all the elements of A, we want to reduce their background. Like I just told you they're the foreground. So I am kind of ignoring the fact that my process said maybe they're kind of background. So what this is saying is don't pick pixels to be in the foreground if you have a strong belief that they're in the background. Don't pick pixels to be in the background if your AI was telling you that they're in the foreground. That's what makes sense. So instead of being positive, you're being negative. You're saying instead of picking guys who have a high AI, don't pick guys in AI who have a high PO. And if you don't like that, another way to think was just I did algebra and I did something. But intuition is not as doesn't have to be as strong. But it doesn't always happen. Sometimes it happens in communication for the negative. So this is just an algebra trick. In this case, there is You could, but we are maximizing over subsets. I want to maximize over a subset. A subset is a cut. That's a clue in your brain. Again, these are all judgment calls. That's one the clues that I think. Right? So I'm maximizing. I'm trying to find a subset that doesn't very good. I want to make it look very. The next problem will be maximizing. Okay. Let's continue. So let's look at another problem where again the flow formulation itself might not be the most obvious one, but actually lead you to a solution. So let's remember an old problem of interval scheduling. We talked about interval scheduling when we talked about video algorithms. Namely, I have a bunch of intervals and I want to schedule a set of them that do not interfere. That they don't interfere with each other, so I can schedule them all at the same time on some shared resource. And we know that if you have a bunch of intervals, and all you have to do is maximize the number of intervals that you pick, then a greedy algorithm will give you the optimal solution. What I maybe did not mention, and I don't remember if I mentioned this, that if your intervals have weights, then a greedy algorithm will no longer work, but a dynamic programming algorithm will work. That's another thing to see. Suppose I have a different kind of interval scheduling problem. Suppose it looks like this. It's an airline scheduling problem. And the setup is something like this. And again, you could say that there are different forms of this problem, and that's true. But this is one form we'll look. So I have a collection of routes. A route is defined as an origin, a destination, a start time, and a duration. We're going to ignore delays for now. Again, this is stylized. And we're an airline. We have a certain number of planes in our fleet. And there's some routes, other routes that we might want. So there's some good routes, like the San Francisco JFK route is a very profitable one for Delta. So they like to have many planes on that, many people are going back and forth. And there's some other routes, maybe from Salt Lake to Boise, which may not be as profitable, but there's some other route they like to maintain. So you want to service all flights. This is the rule. And you can use a plane for 2 flights if it's in the right place and the right amount of gap. Or you can actually get from one. So in other words, if I want a flight to go from San Francisco to JFK, right, and then afterwards I wanted to go from JFK to, Boston, right, then I better make sure that the flight from SF4 to JFK ends at a certain time, enough before the flight from JFK to Boston, so the plane can be cleaned. I'd like to do this, of course, because then I don't have to use extra planes. The more I can use the same plane for flights, the fewer planes I'm going to need overall. And so the question is not so much minimize the number of planes I need. The question is, given all these constraints and the fact that I only have k planes, can I actually traverse all the routes I need to traverse? Now again, this is a kind of a high-level view of the problem. I haven't really fully formalized it yet, but we're going to do that as well as trying to see how we might think about it in terms of flows. And when you look at this and you start saying, are k planes sufficient to traverse all routes? We're not asking for a subset now. Right? We're not asking for what subset of planes is going to work. We're asking for something different. And if you think of a plane as kind of traveling along a path, and a plane is, I'm going to give this weight on. If you think about a plane as a unit of flow, sounds like it's asking, I have some network, and I want to push k, is k units of flow enough to satisfy the demands of the network? Now I'm using words that are codes for things I might want to model. Okay? All right. So let's see what we're going to do. So let's say I have this example here. These are my routes. So the BOS 6 DCA 7 means there's a flight from Boston that leaves at 6 a.m. and reaches DC at 7. I have no idea if this is actually true. I know there's a flight from DC that reaches LAX at 11. That's probably true. Again, we're ignoring time zone issues. This, of course, clearly has changed from East Coast to Pacific time. But that's okay, because I'm going to use a plane for 2 flights, then it's going to be the same time zone. Unless you're in Arizona. Weird. So you have this input here. And so now I say, okay, I have a flight here. I know this flight can hit DCA at 7 o'clock, and it can wait, and it can take this flight here, right? Now I would like to, now what do? I can't use this plane for the Philly flight. I'm not an SFO, and I can't get to Las Vegas. But maybe there was an extra flight there that was not a lucrative flight, but it was a flight that I could use somewhere. That went from LAX at 12 to Las Vegas at 1. So then I could use that, and then I could use that. So this is what I kind of think I'd like to do. I'd like to plan this carefully to say, I am able to use this plane for all these routes here. And of course, when I think about this, now you start seeing, okay, there's something interesting going on. So is the problem clear at this point, what you'd like to do? Again, we're not trying to minimize the number of planes in a fleet. We already have a bunch of planes. Right? We're not trying to buy new planes or anything. What we're saying is, given the planes we already have, given the routes that we want to service, given the constraints on using any single plane for a number of different routes, is there a way to schedule all the planes so that we actually can cover the routes? And a lot of scheduling problems end up looking like flow problems. Not all. Most of them are much harder, but many of them do. Which is another clue in your mind. If you see a problem that starts looking like a scheduling problem, that's a clue that maybe there's a flow formation. Yes?
So, sorry. So the goal is to try to fill all the routes. Right?
Yes.
And that's it. No.
Yeah, so the answer is going to be yes or no, right? The answer is going to be yes, you can satisfy all the routes with your planes, or no, you cannot. There's no other thing you have to do. You're not minimizing, you're not maximizing. It's just a yes-no question, which is another clue, by the way. We've seen flow problems where the answers are the yes or no. Do you remember anything? We saw some recently. But the only question was yes or no. Yeah?
The demand ones, where you have can you satisfy the circulation?
Very good. So now you're thinking, okay, I know there was this problem with circulations and demands, and there the only question was, is it feasible or not? So that's telling us, okay, maybe that's the kind of question we'll look at, because we're not trying to maximize or minimize. Good. So how about we model this problem? So as you say, problems on a feasibility. So maybe you need a circulation. A circulation, as I talked about last time, are these problems where you just have demands and constraints, and you just want to check if a flow exists or not. Because a zero flow no longer satisfies the problem. Because you have, say, vertex demands or edge load bounds or something. So now we're thinking planes are going to flow. Right? They're flowing from route to route. If they're flowing from route to route, and a plane is a flow, and a plane sits on a route, then a route must be an edge. Right? If you're saying that a plane should be a flow, then nothing that goes on should be an edge. So the route should be edges. So if the routes are edges, what are they going to be the vertices? The airports, the cities, right? They're going to be the vertices for us. Okay, so now we're building up a model in our head. Okay, this might be how it works, right? So you have one vertex for every city. You have edges between cities based on routes that exist between them, right? And now a route must be traversed. There's another clue. We have to traverse this route. There has to be flow on this edge. Remember we talked about demands last time? We talked about lower bounds and flow. And we said, there's a way to talk about flow where you must have this much flow on this edge. That's what it's kind of saying here. We must have a certain amount of flow on certain edges, the lucrative routes. There are other routes that maybe we don't care. But for these routes, we do. So that's already a clue now. That's telling us. So then, you have only one plane per route. You're not going to use multiple planes per route. And since a plane was flow, and there's only one plane per route, you want unique capacity leverage. You don't want to have two planes flying the same route at the same time. The route is defined by time, right? The same flight from SFO to JFK in the morning and evening are two separate routes. They're not counted the same. They're two separate edges. Okay? So now we have that. So we have edges, we have lower bounds in the flow, we have capacities and edges. Let's say planes start in the morning and they end at night. So this is a daily routine. I didn't mention this earlier, but think of this as a kind of something you do over the course of a day. So we're going to start in the morning and end in the evening. So that tells you immediately that the source should be morning, the sink should be night. Right? So the source will connect to potentially all the cities, but once you start in this sort of time frame and everything will end up at the sink. Right? So you can connect the source to everything, connect the sink to everything. Because we're saying for any particular day, we don't know which flight to take first. And two routes. Remember, a route was an edge, right? And two routes are connected if we can get from one to the other. So there's going to be, you're going to add extra edges basically between cities. If you can, so basically two cities are connected, you get from one to the other. There's going to be extra routes you can take to get from one city. And that's basically it. So you create a graph that looks like this. You have directed edges, of course, because now this actually is directed. You are not flying between Boston and DC, you're flying from Boston to DC. That's not a problem. You have edge lower bound, you have flow lower bounds on the important edges. You have other connections because you can get from one place to another. For example, I can get from LAX to LAS by a different flight. But they don't have edge lower bounds on them. And I have capacities on all these edges. And now the question becomes for me is there a flow? Of how many units? How many units of flow am I looking for? Anyone? K. Because I have K planes. Each plane is yes.
So what if you had like a flight that's from Boston to DC all day, and then people up in Pittsburgh all day, and then that like Las Vegas Seattle flight?
Wait, what does all day mean here?
Like, wouldn't you want to connect the source to multiple flights because it's not going to want if that was the ideal situation?
Oh yes, in fact, so maybe I should have added more edges. There should be an edge to the source to everything.
Okay.
Yeah, so maybe that the first flight is in the afternoon. Right? Yeah. So we're assuming that, at the end of the day, all the planes can be rearranged to be in the right places. So yeah, so the source can go to anywhere. Yeah, that's correct. In the formulation will do exactly that. Yes.
It seems that the vertices of the graph should be the routes, not
what?
the airport.
Why?
Just from this graph.
But why do you think this should be the case?
Because we are not thinking about when we are flying plane from some place to another place, right? So we are not bothering about the actual flight which is going to happen. We are bothering about how the routes are going to be connected in this problem.
Okay.
Right. So I think the vertices of the graph should be routes.
So that would not actually change the formulation, because if you imagine this, I said there was an edge, there was a flow lower bound on this edge and a capacity of 1. Since this is a single entity, I could in fact contract it and have a vertex now who has a flow lower bound of 1 on it and a capacity of 1. And we actually know how to handle vertex capacities. And you can handle vertex flows, you'll end up going back to this anyway. So I just saved a step, but you're right. There's no intrinsic reason why you can't think of it that way and then rewrite it using the things we talked about last time to convert it to this. So just to wrap up the story, what's going to happen now is that we're going to get this instance of a graph and we're going to run a max flow out of it. And the max flow is going to say your flow is 10. And we're going to look at 10 and we're going to look at k. Is k more than 10? If k is more than 10, then I guess you're happy because you can satisfy the demand, but you're maybe a little unhappy because you have too many extra planes. That's a different story. But if k is less than 10, then you don't have enough, well, not max flow, find any flow. If k is less than 10, then you don't have enough planes to satisfy the demand. Another way of thinking about this is that you push k units of flow from S and see if there's a feasible flow or not. That's maybe a better way to do this. Push k units of flow from S, right? And then see if there's a feasible flow.
You should flip the edges before.
Flip the edges before.
I mean, you want to force one unit between any two edges, right?
Between the black edge.
Before pushing.
Why do I flip it?
I mean, because the way you're assuming right now is.
But the edges are going forward, and I'll push flow forward. That's correct, right?
No, but you want to make sure the one unit always flows through that one.
Right, so okay, very good. So when I say run flow, what I mean is take the problem with edge lower bounds and capacities and do the transformations we talked about last time to make it into a regular flow problem. And then run, so I'm assuming a black box now that you know how to handle edge lower bound. But you're right, you have to do all those transformations. But you see that now if we did not have the tools at our disposal that we saw from last lecture, this would have been a lot harder to capture. If we just knew about max flow and min cut, we could have solved the first problem. But we wouldn't have been able to solve this because this idea of you must push flow on this edge doesn't really exist in a flow problem. It's just in a vanilla flow problem because the flow just goes. But because we know all these transformations and tricks, we know how to force these things to happen without changing the underlying characteristics of the flow problem. And that means our space of models becomes a lot richer. We can try all these different things. And when you look at the homework assignments, you're going to find that you're going to have to be able to learn how to recognize when I need to use this extra feature or not. And for the most part, flows are very forgiving, right? If I want to put vertex capacities, I can do it. If I want vertex demands, I can do it. Edge capacity, I can do it. Anything local, I can do it. If you want to say things like, okay, these two edges have to have the same amount of flow, then you're going to be in big trouble. Then it may or may not work for your particular problem. That's when things got really hairy. So it really depends on the problem and the model you have, and in this case, we're going to solve. Okay, question?
Doesn't each route have to have some demand? Because you can't not have a route without a point.
So I said, remember the edge, there's an edge lower bound?
Yeah.
This edge must have a flow of 1 on it. All these packages must have a flow of 1. That's why this is a feasibility question. Is there even a way to make sure that all these special edges have a flow of 1 when I only have k units of flow? Right? So that's correct. That's part of the model. Okay. And then we have to do a transformation. Other questions? This is quite different from the previous problem, as you can see. That was really a cut thing, where you want the set, and here's a flow thing, which is feasible. No? All good? Okay. So, this concludes all that I will be saying about flows in this class. This is much to my infinite sadness, because there's so many more things I could tell you about flows, but then we'd spend another year in this class and it would not help me very much. There's stuff in the notes that you can read, especially the thing that I regret most not telling you about is the idea of costs. Namely, that you can not only talk about max flows and min cuts, you can talk about min cost flow. Where the idea is that when you push 1 unit of flow along an edge, each edge has a cost, let's call it C. You pay C units of cost for that 1 unit. So if I push F units of flow along the edge, the cost I pay for that is C times F. And again, you can think of many reasons why this might be the case. Some edges are, maybe because it's more expensive to lay the pipe, it's more expensive to transmit the material through it. So there's a cost. There's a cost per unit of flow. So it's not an installation cost, it's a cost of actually running the flow. And the idea of a min cost flow changes your game completely. Your regular flow formations don't work anymore. You need a brand new algorithm. So it's a lot more complicated. For example, a simple case of where min cost flows come up is, suppose I bring my biproduct matching now, as before. Remember the goal was to find a maximum matching? Suppose my goal was instead to find a maximum weight matching, where each edge has a weight, a cost, or a weight, in this case profit, and I want to maximize the profit. Now my flow algorithm is not looking at weight, so it's not going to do the right thing. It's going to pick edges as it sees fit, but they may be very low weight edges. So you have to have a different algorithm for doing this. And again, there are many problems where you want to model precisely that. The idea that things have weight and there are things that are more important than others. And just like when we went from interval scheduling, unweighted was easy to do greedy, weighted needs dynamic programming. Weighted max weight matching is a different kind of flow problem. A completely different kind. And it's something that, again, I made a choice not to cover it, so it's my fault. But there are notes on this, and I will link to them. I would encourage you to take a look. It's a very nice set of tools there. And again, from a modeling point of view, if you know that, in fact, you can actually capture costs on the edges, then that allows you to solve more problems, and you can go look up some standard management cost flow algorithm and just run it. But the thing is, from a modeling point of view, it helps you to know that these things exist, that you can actually incorporate costs on the edges. And I guess that's all I want to say about flows for now. We will transition to a new topic next week. We will be talking about randomization. Namely, what happens to your algorithms when you're allowed to toss coins in the process of running the algorithm? It turns out you can do things that look almost like magic once at the bottom, but it makes reasoning about the algorithm a lot harder. And so we'll see many examples of how you can do it. Okay, so we ended early today. Not a bad deal, but I will see you all next week.